Welcome to today's lecture. In the previous lecture, we had seen how various properties of the derivative help us to analyze properties of the function and analyze its nature. Today, we will be starting to look at some of the finer aspects of how calculus helps in looking at more deeper properties of a function, which will have applications in our economic scenario, how the marginals increase and decrease. So, these properties are captured by properties of the function called being convex and concave. So, to motivate this concept, let us consider the following examples of two functions. So, mathematically let us look at these graphs of these two functions. One function is f, that is this green one, and g is another function which is the red one. So, now the question we would like to ask is, what are the similarity between these two functions and what are the differences between these two functions. So, from the picture it looks like f is a nice continuous smooth function, right. So, there are no corners and there are no breaks. That means, one says mathematically that the f is a continuous and of course, a stronger condition, namely f is a differentiable function. And similarly, g also looks like a nice smooth graph without any breaks. So, one says that g also is a differentiable function. So, both the functions are differentiable functions. This function f is increasing. So, as you move from left to right, the graph of the function is rising, and same is happening for the function g. As you move from left to right, the graph of this also is increasing, is also moving upwards. So, both these graphs are graphs of differentiable functions and both are increasing, but still there is a categorical qualitative difference between the graph of f and the graph of g. And what is the difference? So, if we look at the picture itself, the graph of f seems to be bending away from x axis and the graph of g seems to be bending towards x axis. So, this property of functions, one being bending away and one bending towards, we would like to make it more precise. So, what we are saying is there is a marked difference between the quality of the two graphs, though both are differentiable and increasing. So, geometrically we can say that the graph of f is bending away from x axis, whereas the graph of g is bending towards x axis. So, how do we analyze this mathematically? So, this is a kind of scenario we are looking at. For example, look at this graph, green graph. Here in this portion, the graph is bending away from x axis, while in this portion the graph seems to be bending towards x axis. So, we would like to make this more precise. So, let us look at geometrically what is happening and then try to understand this and make a mathematical formulation of this property. So, I am going to open this graph in GeoGebra and trying to see dynamically what is happening in that. So, here is the graph of the function. So, this is the graph of a function. Okay. So, now let us see what I have done is, because I want to understand this bending towards x axis and bending away from x axis. So, what I have done is I have taken 2 points, say C and H, on the graph of the function, and I am going to move these points. So, let us move this point, say for example, let us move this point C and see what happens. So, if I move this point C on the x axis, so see up. So, what is happening to the red line as I move the graph of the function, as I move the point C? The red line stays above the graph of the function. Same will happen if I keep the point C fixed and move this point H. So, if I move the point H, you see that the line joining the point C and H on the graph of the function always stays above the graph, it never comes below the graph, right. It always stays above the graph of the function. While if I go on the other side, so let us take the point C on the other side here, okay, and bring this point H closer. So, now you see up to certain point, up to this point for example, it is above, part of it is above and part of that is below. So, if I move this point a bit more, so now you see it started staying below the graph. After this point, for example, after this point G, it starts going up. So, what we are saying is that there is in this graph, there is a point, right, which separates out bending towards and bending away. So, what is bending away? Bending away means that the line joining any 2 points on the graph should stay below the graph of the function, and saying that it is bending towards is saying that if I take 2 points on the graph of the function and take the line joining them, that the line joining will stay above the graph of the function. So, that is what categorically characterizes, geometrically characterizes the property that the graph is bending towards and bending towards away. So, bending towards the x axis will mean that if I take any 2 points on the graph of the function, then the segment joining, the chord joining those 2 points should stay above the graph of the function, and other way around on this side when it is bending away, then the chord joining these 2 points should stay below the graph of the function. So, that is what should happen. So, this property, let us try to put this property mathematically. So, this property we want to saying that when saying bending towards x axis should mean that if I take any 2 points, then the line joining them should stay above the x axis. So, this property we want to characterize. So, this is another picture of the same thing. Okay. For example, if the graph is bending, this is bending towards, so the line joining should be away, should be above, right. So, the Lx, the line joining, the chord joining should be lies above, on or above the and similarly it should I am sorry. So, yeah. So, it should stay above if it is to be bending towards x axis, and the chord should stay above if it is to be chord should stay below the graph of the function if it is to be bending away from the x axis. So, this we want to write mathematically. So, let us put a definition that let f be a function defined on a interval I taking values in R, the real numbers. So, we say f is concave upwards, or it is also called convex, if for any 2 points x 1 and x 2 lying on the interval and a point x in between, what should happen? The value of the function at that point, we want to say that the graph is below. So, below means the value of the function at that point should be less than or equal to value of the chord joining. So, this is, if you recall, we had the 2 point formula for the line joining 2 points. So, this will be the value of the function at that point. So, if you want to look at the picture once again, so this is Lx, if you want to say it is below. So, if we take a point x here and take, so this is the value of value on the line joining, and this will be the value on the function joining on the graph of the function. So, the value on the line joining should be below, that is concave down. So, this property we are writing. So, we say concave up if f of x is less, right, the graph is below the chord joining, and then we say it is concave up, or it is also called convex. And we say strictly concave up or strictly convex if this inequality is instead of less than or equal to, it is strictly less than. Similarly, we will say is concave downwards if the inequality is reverse, f of x is bigger, the chord joining is below the chord joining. This is the value of at the point in the chord joining, and this is the value of the function. So, graph is always above the chord joining. So, then it is called concave upward, and we can say strictly concave when f of x is strictly bigger than, then the one adds the word strictly concave up or concave down. Right. So, as we saw in the previous example, there was a point on the graph where the nature of the function changes from concave to convex and other way around. So, we say a point C is called a point of inflection if f is continuous at C first of all, there should not be any break in the graph of the function, and on the there is an interval C minus delta to C plus delta such that f is strictly concave upward on C minus delta to C. That means what? On the left of C it is strictly concave up, and on the right of it on C to C plus delta it is concave downwards. So, this is the point C is the point where strict convexity changes to concavity or other way around. So, the function changes its nature from strictly convex to strictly concave or vice versa. So, that is called a point of inflection. So, this is a point changes its nature. So, the point of inflection for a function is a point on the graph or point in the domain where the function changes its nature from strict. The word strict is important, otherwise constant function will have all very point as point of inflection. So, this is important that strictly concave upward and strictly concave downward on the left or vice versa of that. So, it should change its nature from strictly concave up to concave down or strictly concave down to strictly concave up as you cross the point C. So, let us look at some example. So, let us look at an example of the function f of x is equal to x cube, x is between the interval minus 1 to 1. So, this function we know that f of x cube is a differentiable function, differentiable everywhere. So, no problem comes, right. We are not going to use the property of differentiability. See, in the notion of definition of convex and concavity, we just want to compute given 2 points whether the value of the function at a point is less than or bigger than the value at the line joining them. So, this can be done very nicely without any calculus tool. Let us take 2 points x 1 and x 2 and a point x in between them in the interval 0 to 1. Then let us look at f of x minus f of x 1. So, what is f of x? F of x is x cube, f of x 1 is x 1 cube. Now, using a bit of algebra, we will factorize this thing. So, this can be factorized as x square plus x 1 square plus x 1 into x minus x 1. So, this is called the factorization of a cube minus b cube identity in algebra. Hopefully, you have studied in 10th standard. If not, look at the factorization of various algebraic identities, namely what is the factor of a square minus b square or a cube minus b cube and so on. So, this is the factorization of a cube minus b cube, it is equal to a square plus b square plus a b into a minus b. So, here it is x 1 minus x 1, that is factor here. So, x square plus x 1 square plus x into x 1. So, that is the factorization of this. So, using that we have gotten this f of x minus f of x 1 is equal to this. And this x minus x 1 we can keep it out, here is x 2 minus x 1 that cancels out. Okay. So, we are dividing by x 2 minus x 1 and multiplying by x 2 minus x 1. So, instead of x I have written x 2 now, because and the sign has changed to less than, because x is less than x 2. So, in this if I change x to x 2 we will get less than, right. So, x 2 x 2, x is less than x 2. So, we will get a less than, and multiply and divide by the same quantity x 2 minus x 1, you get this. Now, this expression looks familiar. So, let us write down this expression is it equal to x 2 cube minus x 1 cube divided by x 2 minus x 1, and that we put back the value in terms of the function f. So, f of x 2 minus f of x 1 divided by x 2 minus x 1. So, what we get is that f of x, which was on this side, is less than or equal to f of x plus f of x 2 minus f of x 1 divided by x 2 minus x 1 into x minus x 1. So, that gives us that the function f of x to be equal to x cube, right. Here we have assumed, of course, let us just go back and see, one should be a bit careful here. So, we have taken in x between 0 and 1, that is why every inequality was maintained. Okay. So, this gives that in the interval 0 to 1, the function is strictly concave up in the interval 0 to 1. A similar analysis, algebraic analysis can be made, but to show that it is strictly concave down in minus 1 to 0. So, the function is strictly concave up in this, strictly concave down in minus 1 to 0. So, 0 is a point of inflection, that is a point, it is continuous at that point and it changes its nature. So, that means that that is a point of inflection. So, here is the graph of the function f of x is equal to x cube. So, note that, so if I look at the points on the right side, right, from 0 to 1 onwards, then the chord joining them stays above. If I look on the left side, the chord joining the points stays below the graph, right, and the point 0 is the point where the function changes its nature from strictly concave down to strictly concave up. And note that at this point 0, even though f dash of 0 is 0, this is not a point of local maxima or local minima. The tangent here becomes horizontal. So, the function is everywhere increasing function. So, as you move from left to right, the function is rising. So, it is everywhere increasing function, strictly concave down, strictly concave down in this area on the left side in the green, and concave up in the region which is the red one on the right side of it. So, this is how you decide whether a function is concave up or concave down by looking at purely algebraic nature of this. We could do because our function f of x is equal to x cube is a very simple function, but for more complicated functions such kind of algebraic identities may not be possible. So, one has to devise certain tools which help us to analyze convexity and concavity of a function in terms of the derivative of the function. So, we would like to find out those criteria which will help us to decide whether a point, what are the points where, what are the intervals of convexity and concavity, and what are the points where the function can have a point of inflection. Here is one caution you should have, that geometrically it should be obvious that if there is a break in the graph of the function, that then the function cannot be in that interval, a convex up or concave down. So, what we are saying is, supposing this is the graph of the function, the green one, and at this point there is a break in the graph and graph starts here and goes this way. So, if I look at this part of the graph, then that part of the graph looks like bending away from x axis, right, and this part of the graph looks like bending towards x axis. So, in this part of the graph is concave up, that part of the graph is concave down, but in the whole of the interval I cannot say the function is concave up everywhere or concave down everywhere. For example, if I take a point G in this part of the graph and take a point H and take the line joining them, then what do you observe? You observe that in this part of the graph, the red chord, the segment is below the graph, and in this part it is above the graph. So, you cannot say that in the whole interval domain of the function is concave up or concave down. So, that indicates that if a function is concave up or concave down, then it should be continuous at every point. So, this is only an indication of a result which is actually true, but we will not be proving that. So, it says that if a function is convex or concave in an interval I, right, then it must be continuous in that interval. So, whenever you are analyzing convexity or concavity, you have to ensure that the domain that you are looking at is a interval, and in that interval the function is continuous. Otherwise, you cannot analyze that. So, let us look at one more example to understand what we are saying now. Let us look at the example of f of x is equal to x square. So, we know the graph of this goes like is a parabola. So, it is like a cup which is cup up, a cup, imagine a cup which is kept on a table, and it is at the top is not the inverted cup, it is a cup kept on the table as such, open cup you can think of. So, this is parabola can be thought of that way as right. So, this we know it is if I take any 2 points on the graph of the function, clearly that chord will stay above. So, this is a function which is concave up. So, concave up also rhymes very well with cup up. So, physically cup up is like concave up. So, that is like u or v or whatever want to say. So, the way of remembering is associating that concave up is like cup up. So, what we are trying to say is this function f of x equal to x square is concave up. So, let us look at the slope of this at a different points. If we take a point on the left side, the derivative is 2x, okay, and if x is negative, the slope will be negative, right. So, as you come closer and closer to 0, the slope is negative, stays negative, but at the point 0, the slope becomes tangent becomes horizontal. So, slope is 0, and as you go on the right side, the graph of the function. So, if you look at a point on this side, then 2x, the derivative will be positive. So, tangent is having a positive angle. Here the angle is more than 90. So, it is a negative slope. On this side the slope becomes positive. So, as you go from left to right, for this concave function, the slope goes from negative to positive. So, that means it is slope is a increasing function for this kind of a graph which is concave up. So, this is a general phenomena which happens for functions which are concave up and gives us conditions in terms of the derivative. So, we are saying that if the function is concave up in an interval, then the derivative must be a increasing function. So, that theorem we will state it in the next lecture. So, this example f of x is equal to x square is indicative of the result that if its function is concave up, then the derivative must be increasing. So, we will look at it in the next lecture. Thank you.